All right, so we're going to start with page 110, number 17. Okay, so here it says that grocery store determines that a new cashier can scan n items with respect to the number of minutes. They want us to find the derivative of n with respect to t. All right, and then according to this model, does the cashier ever stop improving, and why? Okay, so let's start with the derivative. So n of t is given by 20 minus 30 over square root of 9 plus t squared. Okay, so the first thing we have to do here is just find the derivative. That's what they want us to do in A. So here, the derivative, and again, we assume it's with respect to t, because that's what the variable in the equation is. Okay, and now here, pretty easy, because the derivative of 20 is just 0. And this is where I would probably just do it in my head, but it might not be a bad idea for, especially if you struggle with any part of this, it might not be a bad idea to rewrite this as 20 minus 30. And here you have 1 over the square root of 9 plus t squared, which can be written as 9 plus t squared to the negative 1/2. Okay, so if you have even a bit of a hard time kind of seeing that, just looking at the function, then take the couple of seconds that it takes to just write it out in this fashion here. Okay, so here, this, again, we said derivative is equal to 0. We've got negative 30 is just a constant, so you can pull that out of the derivative. And so now we're just taking the derivative of this part here. And of course, we're going to have to use the chain rule. So this is our u. What's the derivative of u to the negative 1/2? It's negative 1/2 u to the negative, well, sorry, I won't write u. I'll just put it directly as 9 plus t squared. Okay, and then negative 1/2 minus another 1 is negative 3 over 2. And then, of course, we have to multiply that by the derivative of u with respect to t, which is just going to be 2t. Okay, and so there's a derivative unsimplified. But then when I look at B, it says, according to the model, does the cashier ever stop improving? Okay, so let's think about what n tells us. It's the number of items with respect to the number of minutes the cashier is working. And so the derivative would be the rate at which the number of items is changing. Okay, so I guess if the rate of change at any particular point is positive, it means the number that they're cashing out is increasing. And if it's negative, slope of the tangent would be decreasing. So it's going down at that point. So what they want us to know is, does the cashier ever stop improving? So I guess that would mean that the slope of the tangent at some point would have to be negative, or I guess could even be equal to 0, because at that point there, they're neither improving nor getting worse. Okay, so because I have to make some sort of determination based on the derivative, I think it's worth now actually simplifying this. Okay, so here, this 2 in the denominator cancels out with this 2 in the numerator. Here, these 2 negatives become positive. So let's see what we would be left in the numerator here. So it looks like I would be left with 30t. Okay. And then because this is a negative exponent, I can just write that in the denominator. So it would be, and I could just write it as 9 plus 9 plus t squared to the 3 over 2, or write it in square root form. I don't think it's really going to matter. So 9 plus t squared to the 3 over 2. And this is a simplified version of my derivative. Now, of course, what we have to remember is that t here is going to be strictly greater than or equal to 0. And what I notice is that So I'll just take a look here. The answer, we'll take a look at the textbook answer later on, okay? But let's just finish off this question here, okay? So here, essentially what we have to show is this derivative ever going to be 0 or negative? Well, remember, t is greater than or equal to 0. So obviously this is 0 at 0, but that's right at the beginning. But we notice that for every other value, this is going to have to be a positive number because 30 times t is going to be positive. The denominator is always positive, regardless of what the input of t is. So this is greater than 0 for t greater than 0. Therefore, it looks as though cashier is always improving. Okay. Now, I'm not going to deal with this any further now. But, you know, just because they continue improving doesn't mean that they're going to be scanning that it goes towards infinity. Okay, it could be leveling off at some point. Who knows? That's where we would have to do a little more investigation about what the graph of this thing was looking like. Okay, so it looks as though there might have been some issues with the derivative in the textbook. So, you know, that happens. All right, any questions on this here on finding the derivative? Now, somebody asked, could you use the quotient rule? Yeah, you can, but it really is sort of much more, you know, a much bigger, you know, set of ammunition than you really need here. You know, it's easier to just do it using the chain rule, but yes, well, actually you'd have to use the chain rule anyways, but yeah, you could use the quotient rule, it would just take longer. Okay, any questions on number 17? Nope, okay, so let's move on now. We had 110, number 23C, okay? So page 110, number 23C, and let's see what that is asking us for. So here it says determine which functions are differentiable. Oh no, sorry, 23C. At what x values is each function not differentiable? Explain. So I gave you, I guess, 23C. So let's look at the function itself. So it's the square root of x squared minus 7x plus 6. Okay. So I guess there's going to be a few things that we have to look at. So first of all, clearly the function is not differentiable anywhere that f itself doesn't exist. So I would almost say, let's start with that. Let's figure out where f doesn't exist. And here, since I have a square root function, well, what am I going to have to do? I'm going to have to figure out when the function inside the square root is greater than or equal to 0. Okay, so what I'm going to call sort of part 1 here is let's figure out where the function's not even defined. So that's where this denominator, that's where this input into the square root is less than 0. Okay, so let's solve x squared minus 7x plus 6 less than 0. And here, you know, polynomial inequality. Hopefully remember from what we studied last time that the easiest way to do this is to just factor it and quickly draw a graph. So this, I think, is easily factorable. It's just going to be x minus 6, x minus 1 less than 0. And here we know that the only places it can change sign is at 1 and at 6. And since it's a positive leading coefficient, my quadratic looks like this. So that means anywhere between 1 and 6, okay, this function is not differentiable. Why? Because it's not even defined there, okay? Now, one thing we could do is we could try to draw the graph of this function to see if there's any other places where there might be cusps or issues like that. But this is not a function that at this point is that easy to graph. So what I'm going to do is let's just take the derivative and let's see where the derivative doesn't exist. Okay, so if we take the derivative, so here I'm not going to rewrite it as a square, as an exponent 1/2, because I think we can do that in our heads. So here it's, you know, u to the 1/2. So it's 1/2 u x squared minus 7x plus 6 oops, plus 6 to the negative 1/2, and then times the derivative of u with respect to x, which is just going to be 2x minus 7. Okay, and now because again, like before, I need to make some sort of determination based on this derivative, I think it makes sense to simplify it. So 2x minus 7. And here, this 2 is already in the denominator. This is going to bring everything into the denominator. And I have the square root of x squared minus 7x plus 6. So as before, anything that makes the thing inside the square root negative has to be eliminated, but I've already eliminated that. But what's the other problem now that presents itself? Can somebody tell me what the other problem is that I have to worry about? There you go, is we know that whatever's inside the denominator can't be equal to 0. So here, the function is defined at 1 and 6, but here I'm going to have to eliminate anything that makes the denominator 0, and that's going to be 1 and 6. Okay, so it looks like here, where is the function not differentiable? So my answer is going to be, okay, so not differentiable. And let's remember my shorthand for differentiable on 1 to 6, but I'm going to have to include those two. Okay, and here y gives an explanation. Well, 1 to 6, you know, f and f prime not defined. Okay, and then at x equals 1 and x equals 6, f prime not defined there. So that's why I had to also eliminate those. Okay, so we see here, it's just about, you know, using now an analytic approach to determine where the derivative doesn't exist, as opposed to some of the other questions where we were looking at a graph and used a graphical approach. Okay, any questions on this one here? Okay, no. So let's move on. So now we're going to another page. So I think the next page we're going to go to is 156.28e. 156.28e. Okay, so. And so here they're asking us to calculate the second derivative, and at a particular value of 4. So here they give us f at x is equal to square root of x plus 5. And here they want us to find the second derivative at 4. Okay, so I guess the trick here is to first find the second derivative, and then we can specifically find it at the value x equals 4. Okay, so, you know, let's go ahead and do that. So f prime of x. So here again, I'm not going to rewrite this as x plus 5 to the 1/2, but if it helps you to do that, hey, it's a good investment in time. So here, derivative of u to the 1/2, just 1/2 u, which is x plus 5 to the negative 1/2, times the derivative of u with respect to x. Okay, there we go, unfrozen. So derivative of x is 1, derivative of 5 is 0, so times 1. Now, again, you might sort of say, that's a little funny that you know, even though it's equal to 1. Well, it's because I want to make sure that I keep that, you know, the algorithm going so that I don't forget to take the derivative of the inside when it's absolutely necessary to do so. All right. Now here, normally I would say simplify, you know, bring this to the denominator because of the negative exponent. But I know that since I need to take another derivative, you take this thing, this is a much nicer form to use than putting it in the denominator, and then I'm going to have to bring it back up into the numerator. So in this case here, I'll leave this as is. So again, remember 1/2 is just a constant times. Okay, now let's find the derivative of this thing. So again, u to the negative 1/2 is negative 1/2 times u, which is x plus 5, and negative 1/2 minus 1 is negative 3/2. Okay, times, again, the derivative of x plus 5, which is just 1. Okay. And now, whether you simplify this or not, I guess maybe let's do that here. So it looks like the only thing I'm left with in the numerator is the -1. 2 times 2 is 4. And then here, I think what I'll do is, given that I'm looking at what I'm going to be inputting into my function, I'd really like to keep the square root first. So I'm going to take the square root of x plus 5 first, and then I'm going to cube that. Okay, so 3 over 2, remember, you can do it in either direction. I could first cube it and then take the square root, or take the square root and then cube it. And usually I'm going to use this when I'm calculating, because square roots simplify, cubes make things more complicated. All right, so let's calculate that. So now f double prime at 4. Okay, and by the way, I hope you're also looking at my, at the notation that I'm using and what I'm writing, what I'm not writing. Okay, so here, what do we have? We have -1, 4 times square root of 4 plus 5 cubed. So -1, 4 times, and this is square root of 9 is 3. 3 cubed is 27. And so here, this looks like -1 over, so 80 plus 28, I guess 108. I'm not mistaken. Whoop, there we go. So it looks like that's the answer there. Okay. So step number 1, take the first derivative. Okay. In this case here, simplifying was, wasn't necessarily the best thing to do. Leave it in this form. Take the second derivative. And once you have the second derivative, input your value. And just be careful about the arithmetic. Okay. Any questions on this? Nope. All right, so let's move on to, I guess next will be 260. So 260, number 5. Okay, so here it says determine all the values between 0 and 2 pi inclusive for which the slope of the tangent of the function f is 0. Okay, so common type of question here. I guess maybe one thing that's a little different is it involves trigonometric functions. So here at page 260, number 5. So the function we're given here is, is it sine x tan x, sine x tan x, and we want to determine where the slopes of the tangents are equal to 0. In other words, we want to look at when f prime at x is equal to 0, because that's what f prime represents, the slopes of the tangents. All right. All right, let's take a look at this here. So I'll start by finding the derivative. F prime at x is equal to, so derivative of the first, cos x times the second function, then plus the first function, sine x, times the derivative of the second function, which is secant squared x. All right, and we want to set this equal to 0, but of course we're going to want to try to simplify this as best as we can. All right, so here I would say let's put everything into sines and cosines. So sine x over cos x, and already some nice stuff happens. Okay, plus, and then here I guess this is going to be sine x over cos squared x, since secant is 1 over cos. And so what does that give us here? Sine x plus sine x over cos squared x. Oh, I guess I could have kept that cos x there. Doesn't matter. So here, this looks a lot like a rational equation. Okay, so what I could just do is just multiply both sides of the equation by the lowest common denominator, which would be cos squared x. So obviously, if I multiply the left side by cos squared x, I just get 0. So here I'm going to have sine x cos squared x plus sine x, okay? And then here, I see my common factor, sine x times cos squared x plus 1. And so here, what are the two things? Let me finish up here so I save some space. So sine x could be equal to 0, or cos squared x plus 1 is equal to 0. So here, when is sine x equal to 0? And I think I'm only looking at 0 to 2 pi. So sine x is equal to 0 at 0 and at pi. Okay, so there's two answers there. And here I can already see something interesting is going to happen, because when I try to solve this, I end up with a square being equal to a negative number. So here, there's no solution that looks like from that portion of the equation. And here, this is where I go back and check, are they looking for points or just x values? And here they're just looking for x values. So there's my answer done. Okay. So here, really nothing fancy. I just had to be careful about, taking my derivatives, obviously, and doing my algebra correctly. But really, this turned out to be kind of like a, fairly easy trig equation, like we would have solved last semester. Okay, but I would say even easier than most of the ones that we had solved. Okay. I guess if you need particular trig identities, I'll give them to you. But definitely the trig derivatives you will not get. Sine, cosine, and tangent, you need to know those trig derivatives, okay? All right, any questions on this one, number 5?
Tony, I have a quick question.
Yep.
How did you get, I don't know if this seems a dumb question, but how did you get sine x times cos squared x plus sine x? Because I thought you had to factor out the sine x from sine x plus sine x divided by cos squared x. And so it would just be sine x multiplied by 1 plus 1 over cos squared x.
That would have worked too. I just decided to get rid of the denominator by multiplying both sides by cos squared x.
Oh, right, I see. Never mind.
When I multiply, I multiplied this by cos squared x, and I multiplied this by cos squared x. Again, what you had suggested would have worked just as well. Maybe even one less step, but I just figured because then what happens, you get your sine x cos squared x, and then when I multiply to this one here, the cos squared x's cancel out, and I'm just left with something that doesn't have a denominator. Okay, so it was just to kind of simplify the equation, which was a trick we saw when we worked with rational equations in the past. All right. Okay. So let's go to 263. So 1D, and somebody asked for 2D. So I guess we might as well just do 2D. While we're at it, 263, you have time to, okay, let me check at the end if we have time, because it is getting a little, we're already almost halfway through the hour. Okay, 263, 1D, I think was the first one that was asked. So 1D says differentiate the following. So here we've got y equals e. Okay, and we got this big thing in the exponent, negative 3x squared plus 5x. Negative 3x squared plus 5x. Okay, so in the end, this one's fairly straightforward, because we see a composite function involving negative 3x squared plus 5x being the inside function, and then that output gets put into the function e to the x. Okay, so if I'm taking the derivative here, okay, first I'm going to take, what's the derivative of e to the u? Just e to the u. So e to the negative 3x squared plus 5x, then times the derivative of u with respect to x, which is just going to be negative 6x plus 5. Okay, and just leave it like that, because this is certainly the type of question that I'd be asking for you to not simplify. Okay, and let's just quickly do what was it? 2D. Might as well just do it all in the same one here. So 2D, the derivative of x to the 4th times 2x. So y equals x to the 4th times 2, not 2x, 2 to the x. Okay, and again here, I see I'm going to have to not use the chain rule, but I will have to use the product rule in this case here. Okay, So I'm just going to follow the product rule, derivative of the first, 4x cubed times the second function, 2 to the x, plus first function, x to the fourth, times the derivative of the second function. And since this is an exponential function whose base is not equal to e, the derivative is given by itself, so 2 to the x, but there's this extra factor of ln2 because 2 is the base. Okay. And again, you could simplify this. More than likely, I'd probably say not to simplify something like this. So you may have to simplify some, Now, again, hopefully you recognize certain tricks like this one here that we use to simplify. Okay, and in this case here, I just look for common factors. So it's really nothing too fancy here. I see they both share 3 factors of x. They share a factor of 2 to the x. Okay, and so here what you're left with is actually pretty straightforward because it looks like you're just left with the 4. And here plus, well, you've got ln2 is still there, and then you have one of those factors of x, and there you go. Okay, so this is one of these where I could ask you to say don't simplify, I could say simplify. This would be one of those where you could expect either one. All right, any questions on these? No. All right, so let's move on to, so we did that one, So it looks like we're going to go to some of these questions from the sheets. All right, so let's do the one from the unit assignment. So number 3. So I just need to bring that up. Give me a second. So number 3 on that. Yeah, let's take a look at these here. So this is unit 2, assignment 2, number 3. Okay, and as soon as you see one of these, okay, you should be thinking one of 2 things. Okay, and sometimes both. Is you're going to have to do some work with some trig identities. Now, again, these would be trig identities that I'm going to use here that I don't really know that I feel you need them because they're pretty straightforward ones, like tan being sine over cos. That really is something we should know. Okay, and the other thing you should keep in mind, okay, especially when you're seeing, say, this first one, when you're seeing the limit as x approaches 0, you might be thinking that you're using one of those special trig ratios. All right. So here we have 2 tan x over x secant of x. All right. And I notice that the numerator is approaching 0 because tan of 0 is 0. And of course, the denominator is approaching 0 because x approaches 0. So I know this limit has issues, but might exist. Okay. So what I'm going to do here is I'm going to try to simplify it and hopefully get to something I can work with. Now, right away, because I see this x in the denominator, I'm hoping you're thinking, at some point I may have to use sine x over x, that limit that we know. Okay, but let's not get ahead of ourselves. Let's do some work here. So here we've got 2 sine x over cos x. Okay, and then here x over cos x. All right, so let's maybe do a little more algebra, even though you might be seeing where this is going. So I'll divide by multiplying by the reciprocal. So I've got 2 sine x over cos x, okay, times the reciprocal of this here, which is cos x over x. And I see here that the cos x's cancel out. So that worked out pretty nicely. And what I also notice is that I've got a sine x in the numerator and an x in the denominator. And I know what the limit of sine x over x approaches as x approaches 0. So A, I know it exists. Okay. So that means that this constant can be taken out of the limit. And what am I left with in the limit? Sine x over x. So here, since limit exists, so that's why I can do it. But not only do I know that this limit exists, I know what its value is. And so in the end, this limit is just equal to 2. Okay, so that's it. Okay, any questions on this one here? So this really was just remembering some pretty basic identities, doing some, I would say relatively straightforward algebra, and recognizing that, hey, I know what the limit of sine x over x as x approaches 0 is equal to. Yes, Arthur?
Yeah, for me, like I had to look up how like I'm supposed to do this question, and they
Yeah.
told me about this rule called L'Hopital rule.
So we have not established that.
Yeah.
So you can't use it
I
unless
can't use it.
you're going to take the time to prove it on the test.
No,
And I
alright.
probably wouldn't try because it's a bit of a complicated proof. So
Yeah, so okay, all right.
yeah. So in the end, you would be expected to do it by using trigonometric algebra. Okay. All right. So let's look at B here. And B is the limit as x approaches 0 of cosecant of x minus cotangent of x all over sine of x. Okay. Now here I see that the limit of the denominator is approaching 0. So I guess here I'd have to do a bit of work to figure out what's going on in the numerator. So I think I'm just going to try to simplify it and see where it takes me. All right. So again, when I look at the, at least the initial trig identities I need to use, they're really not, nothing fancy. Cosecant is 1 over sine x. Okay, and then here cotangent, hopefully you're seeing right away something really nice is going to happen because, hey, they have the same denominator. So it means subtracting these is actually going to be pretty easy. Okay, so let's do that here. So I have 1 minus cos x over sine x all over sine x. Okay, now in principle, I would say you should start getting comfortable that this here can just go into the denominator. But if you're not 100% comfortable with that, or you find yourself sometimes making errors, remember what this means is it's 1 minus cos x over sine x times the reciprocal of that times 1 over sine x. So in the end, where does that sine x end up? In the denominator. So 1 minus cos x in the numerator and sine squared x in the denominator. Now this is where, and certainly that, you've got your trig identity sheet with you. This is where you have to do a bit of work. This is why we needed to learn how to work with trig identities last semester. One of the reasons here is that at this point, you still have a problem. Numerator is approaching 0, denominator is approaching 0. But hopefully what you see is you go, hey, 1 minus cos x, and I've got a sine in the denominator. But because it's a sine squared, I can easily turn this into an expression that's got cos in it. Number 1, I can rewrite sine squared x as 1 minus cos squared x. So at least I'm working with the same trig ratios. And this is where, again, you think about the trick that we used at least a few times last semester when we were looking at trig identities, is this represents a difference of squares. So it means I can factor it like a difference of squares. Oops, cos x. This can be factored as 1 plus cos x times 1 minus cos x. And lo and behold, look at that. They cancel out. And so in the end, it looks like we may just be able to evaluate, show that it exists and evaluate it, because now, oops, that should be plus. Does the denominator approach 0 anymore? No, because cos x approaches 1 and it's 1 plus 1. So this is just equal to 1/2. Okay. So this one here, relatively straightforward in that, there was nothing too fancy with the trig identities. And then you saw that you had the limit of sine x over x approaching 0, which the value of. Here, a little more work involved, a little more identities work. So you never had to use one of the special limits, but you did have to use your knowledge of identities to simplify this expression to the point where you could evaluate it. Okay. So I would say, this is kind of like a medium type question of this type. This is, a little more difficult. Any questions on these?
I have just a quick question.
Yep.
We are gonna have the trig identity sheet with us, right? If
I guess, yeah, you can have it if you want it. There's no,
Okay.
I won't stop you from using it.
Okay,
Okay.
great.
All right. So let's move on. The next one was Unit 2, Lesson 6 homework. So let me just go to that. Unit 2, Lesson 6 homework. Number 1. Okay, so this is Unit 2, Lesson 6 homework number 1. All right. Oh, and this might be the one. I actually think there might be a mistake in my solution. Maybe I think I have 3. It's supposed to be 0.3 or something like that. Whoever asked this, is that what the issue was?
No, I
okay.
just don't know how to do it.
Okay, there you go. But I think, I don't know, we'll check to see, but it looks like I might have been off by a factor of 10 somewhere. So I probably didn't, but we'll see, maybe I was right. Okay, so it says the half-life of strontium-90 is 29 years. Write a model for the remaining strontium-19 with respect to the time using base E. How quickly is the amount decreasing after 20 years if you start with 20 grams? Okay, so let's start with the model. Okay, so what we know is the half-life is 29 years. So what this means is that in 29 years, whatever the initial amount is, it gets turned into half that amount. And since I'm insisting on you using a model with base E, it means that my amount is going to be expressed given a model of this form here. So we know that radioactive decay is exponential, but I'm insisting on using this model with base E. So this tells me that in 29 years, so when T is equal to 29, that initial amount is going to get turned into half of that initial amount. Okay. But what's nice about this is regardless of what the initial amount is, I can still solve this equation for K, because that's my goal here. When I'm looking for a model of this form, essentially what I'm trying to solve for is that K value. And because it doesn't matter whether I started with 100 and I end up with 50 or 1,000 and I ended up with 500, in the end, that initial amount just cancels out. So what I'm left with is 1/2 equals E to the 29K. And now I can just solve this. It's a relatively easy exponential equation. And since my calculator can calculate natural logarithms and I have base E, I might as well use the logarithm with base E, which is of course what we call the natural logarithm ln. So I'm going to take ln of both sides. And again, I'll just write, normally I wouldn't write this out, but ln of E to the 29K, because these are inverses of each other. We just have 29K equals ln of 0.5. And so K is ln 0.5 over 29. Okay, so that means that my model is A equals A naught, whatever the initial value is, E to the, and this is a fairly simple thing here, so I might as well just leave it as is, ln 0.5 over 29, so I don't have to work with an ugly that's what I'm looking for, approximation. Okay, so there's my model. Now, the second part of this question says, how quickly is it decreasing after 20 years if you start with 20 grams? So this is where now, since they're asking me for the rate of change, I'm actually going to be working with the derivative of this function here. Okay, so here I've got my function a equals, now here I'm starting with 20 grams. So this is the model I'm working with, and I just want to take the derivative of this function. Okay, now 20 is just a constant, so I can bring it out of the derivative, and now I'm taking the derivative of this thing here. Well, I have to use the chain rule. So what's the derivative of e to the u? Just e to the u. So e to the ln 0.5 over 29 times t, okay, times the derivative of this function up here. But remember, ln 0.5 over 29 is just a constant. It's just a number. So if it was the derivative of a 5t, it would just be 5. If it was the derivative of 10t, it would just be 10. So what's the derivative of this function? Just ln 0.5 over 29. So ln 0.5 over 29. And this is my derivative. And now I'm going to determine this derivative at the 20-year mark. Okay. And so now I need to stick this big ugly thing into my calculator. So I'm going to try to be as careful as possible. So please, if you notice I do anything odd in my calculator, let me know. So what I'm going to suggest we do is let's start by calculating this more complex thing here. So we have E, and my calculator opens up a bracket automatically. If yours doesn't, I would strongly recommend that you open one up. So here we've got ln 0.5, okay. Then we've got times t equals 20. Oops, I'm just gonna, even though I don't really need it, I'm gonna put the times 20 and divided by 29. And press equal. Okay, so that's this part here. Now I'll multiply it by 20. Okay, then I'll multiply it by ln of 0.5. And then lastly, I'll divide that by 29. And there you go. It looks like, so that was definitely, I made a mistake. I suspect I might have accidentally put 200. Oh, yes, because I think the original question had 200 and I changed it to 20. Oh, that makes sense now. Okay, so here about negative 0.3. So here, negative 0.3. So that means it's decreasing at about 0.3. And here we're talking about grams, and our t value is here at about 0.3 grams per year. Okay, so sorry about that little mistake in the question. Okay, any question on this here? So this is about understanding that this is the model that we're talking about when we're talking about base E. First step is often to calculate that K value and then, you know, use the model as needed. All right, so I've got, I guess, a bit more time. So let's, somebody earlier on, why did we have to take the derivative and just plug in the calculator? Well, remember, when you're calculating, you can't, let me give an example here. Okay, so let's say you have f at x equals x squared plus 7. If you want to find the slope of the tangent, if you want to find f prime at 3, you don't first input 3 into the function and then take the derivative. You'd always be taking the derivative of a constant. You'd be getting 0. So here, what we do is first we find the derivative function. And once we have the derivative function, then I can input the value of 3. Okay. So we need that derivative of function. So we need that derivative function before we can use it to calculate the slope of the tangent and any x value. So does that answer your question? Okay. So before we take a look at that one there, I think there was one earlier on. It says, could you do number 4A on unit 2 lesson 4 sheet? So let me look at unit 2 lesson 4. So the homework, I think that was Estella, is it the homework sheet or the actual lesson sheet? Oh, I have to go down now. Oh, the homework. Okay, so unit 2 for lesson homework. Okay, and you asked for, I already forgot, 4A. So 4A. All right, so this is unit 2, lesson 4 homework, number 4A. Okay, and this is probably wouldn't give you something with an absolute value in it, just because we didn't spend as much time as I normally would have spent on those types of questions, but I think we can figure it out here. So here we want to take the limit as x approaches 0 of sine x over absolute value of x. Okay. So the problem with working with this here, so obviously we've got, you know, both numerator and denominator approaching 0. Okay. But the issue is what I know is the derivative of sine x over x as x approaches 0, not the absolute value of x. So as we almost always do when we're working with, say, limits or, you know, derivatives of questions that have absolute values, is I rewrite this as a piecewise function and then consider the limit from the left and the limit from the right. But we know how to write root x as a piecewise function. We know that it's at 0 that it's going to change its equation. So it's going to be equal to sine x over x if x is greater than 0. Notice here I don't put equal to 0 because clearly this is not defined at 0. But then what's this going to be equal to when x is less than 0? What is the absolute value of x? How were we able to write it as a piecewise function? We were able to rewrite it as negative x, because if the x value is negative, how do I make it positive? By sticking a negative number in front of it. Okay, so you see what I did is I just turned this function into a piecewise function and it changes equation at 0. But that means it's defined differently from the left of 0 here to the right of 0. So that's why I'm going to have to take the limit from the right. Okay. And notice here, when I'm greater than 0, I'm working with this equation. But hey, I know what this is equal to. That's just equal to 1. That's my special limit. But when I take the limit as x approaches 0 from the left, I have to work with that function. Okay. But I've got this -1 stuck there. But remember, this is just the same, you know, that I put the negative sign in the denominator in front of the expression. They're the same. So this is like having a constant multiple of -1. And since I know this limit exists, I can take the constant out of the limit. And hey, look what I'm left with now. Whoops, I forgot to write from the left. And look what I'm left with, that limit that I know well, -1. Is the limit from the left and right equal? No. So here does not exist, since limit as x approaches 0 from the right is not equal to limit as x approaches 0 from the left. Okay. So I would be more likely to give you questions like, you know, part B here, or the ones that were in the assignment, than this one here, just because we haven't worked really that much with absolute values. But this one here is a pretty simple one, you know, but it is probably not the type of question I would ask. Okay. So somebody asked for page 263, number 8. Page 263, number 8. Okay, let's see if I can fit it on the bottom of this sheet. Page 263, number 8. And let's see what we have. It says, determine the equation of the tangent to the curve defined by that is parallel to the line represented by 3x minus y minus 9. Okay. So what we're looking for is a tangent that is parallel to Let me write it down here, 3x minus y minus 9. Okay, so of course we know that being parallel to this line means they have the same slope. So here, if I rewrite this in slope-intercept form, we have y equals 3x minus 9. So that means the slope I'm interested is 3. Okay, so I guess the first thing I need to do is to determine the x values or x value where the function y, which is given by what is it, x minus e to the negative x. Okay, I need to figure out for what x values this function has a slope of 3. So if there's more than one, then I might be finding 2 equations of tangents. And if there's only one, I'd be finding just one. Okay, so let's start with that. Let's take the derivative. Okay, so here, what do we have? Derivative of x is just 1 minus, here, again, I'm going to have to use the chain rule because I don't have e to the x. I have e to the something more complicated. So derivative e to the u is e to the u, okay, times the derivative of negative x, which is just negative 1. Okay, so here's my derivative, but I'm interested in determining when the derivative is equal to 3. So that's why I'm going to replace that left-hand side by 3, because that's what I'm trying to find. So what are we left with here? We're left with 1 plus e to the x, whoops, e to the negative x. Okay, let's bring the 1 to the other side. So 2 equals e to the negative x. And hey, this is what I like, having a single exponential expression equal to a number. So now I can take the logarithm of both sides. So ln2 equals, again, ln of e to the negative x, just cancels out the e. I'm just going to have negative x. And so x is equal to negative ln2. Okay, so here we're seeing how, again, why we needed all those little strategies and tools we learned in advanced functions, because now I need to just apply them, you know, almost without thinking. You know, this is just a simple exponential equation. But of course, if I want to determine the equation of the line, it's not enough to just have the slope and the x value. I also need the y value. So now I'm going to put this into my function to find the y value when x is equal to negative ln2. Okay, so let's see what that gives me. It gives me negative ln2 minus e to the negative of negative ln2. Okay, and let's see if we can simplify that a little bit. So here, negatives cancel out. And I realize, hey, what's e to the ln2? That's just a, these are inverses of each other. So that's just going to be equal to 2. So I've got negative ln2 minus 2. And this is where, you know, this is kind of where point slope form comes in handy, because I don't want to solve stuff with these values. So I'm going to use point slope form. So what's the equation of the line? Remember, it's y minus whatever the y value of the function is here. So negative ln2 minus 2, okay, equals the slope times x minus whatever the value is here. So x minus negative ln2 is going to be x plus ln2. And now, usually it's kind of nice to just bring this to the other side. So y equals 3 times x plus ln2, okay? And it's just going to be plus whatever this thing is. But of course, plus this is just going to end up being minus ln2 minus 2, okay? And there's the equation of my line. If you really insist on multiplying it out and simplifying to slope-intercept form, you can certainly do that, okay? Now, look at this here. Again, maybe part of you is saying, well, that actually doesn't look that complicated. But what I want you to try to do is I want you to see through the fact that the x's and y's were not the nicest of numbers. The process was exactly like any equation of a line. We find the derivative, we determined what x value has that particular derivative, and then once you have the slope and the point, you just stick it into one of your linear equation models. Okay, it just so happens that the you know, the coefficients are not the nicest things in the world. All right. Any questions on this here? Okay, so I think we've done quite a lot of questions today. So I think we'll stop there, or I'll stop the recording. If anybody has